welcome everyone to this live conference given by our distinguished colleague, Professor SAAD MEKHILEF. We are very happy at UTBM because we are able to host Professor MEKHILEF for 1 month to do research together, maybe build joint collaboration, and so maybe you can have an MOU, exchange student and stuff. Yep. And we are happy to organize this seminar, which is on a power converter for renewable energy integration. Professor MEKHILEF has 2 affiliations. He is distinguished professor at Swinburne University in Melbourne, Australia, and he's also from University of Malaysia. So we are very happy to welcome you here. I will give you free time to introduce yourself. Tell us what are you working on, what are the projects in the other side of the planet.
Right,
Let's see, Australia, you are in the summer over there.
Yeah, we are summer
it's
now.
Very cold over
it's
here.
Very hot.
So the floor is yours.
Okay. Thank you very much, Professor Mohammed, for the introductions. And first of all, I would like to thank UTBM for hosting me for this event. And I'm very happy to be here and to meet colleagues, researchers. Special thanks to Prof. Mohammed for doing all the administrative process. You know, it's a lot of paperwork we have to prepare and to make things happen. But in the end, we made it. And I used to work with Professor Mohammed for quite some time. We need to know each other we met in a few conferences, and we want to bring this relationship to another step, to another level. And that's the reason for my visit to this institution. Because we believe we want to see each other and see what we can do together, you know, in the lab. So, and I'm very happy to see, I think the last 3 weeks, we have been working together and identifying areas of collaborations, which includes student exchange, PhD students, we call dual PhD programs, which we are proposing. I hope UTBM will support that. And from Australian side, also they are very happy actually to work and collaborate to come to Europe, especially during summer, maybe summertime. All right, so actually maybe a bit confusing. I'm from Australia or from Malaysia, you know. So just to explain this, so in what I call the English-speaking countries, professors with double affiliation is very common. You can move around. So actually, I am like based in Melbourne, but I'm still having a laboratory in Malaysia because I've been working in Malaysia for quite some time. So I have a research lab where I have 25 researchers working there, and then also we're having a lab in Melbourne. So we will have this visits, movement of students, dual PhD programs, and both of institutions will benefit. Okay, so that's how it comes this. So what I'm going to share with you this afternoon or this evening is what I'm working on actually is on the power converters. I am power electronics person, you know. I am my work mainly on power electronics, where we design converters, inverters, and we apply them for renewable energy applications such as photovoltaic systems, wind applications. That's actually basically what we are working on. So let me give you some introduction. You know, energy and environment, very complex equation, even higher than the 3rd order differential equation, cannot be solved because they are related, energy and environment. In order for you to get good life, you need the energy. When you use energy, you will impact the environment. So it is a very complex relationship, and scientists around the world have been trying to make this relationship very, what I call, very smooth and friendship, rather than always conflicting. And most of the part of the world still not yet actually reached to this solution. The question is how you can meet your energy need without impacting the environment. Not impacting the environment at the moment, but impacting the current and the future generation environment. Because what we are living today, what we are going to do today, the impact will come And I think, I don't know, you have heard about Australia. 2 years ago, we have bushfires. A lot of fires. This year in France, everywhere. You can see the impact of climate change. And then now, this year in Australia, we have a lot of floods. Never happened in the last 100 years. Never happened this kind of floods. And that actually triggers the questions of the way on how we are using the energy. So the world population is increasing. By 2050, it's expected to reach 9 billion. So I'm not from the statistics department, but for me, I look into this from the energy needs for these people. 9 billion people will need energy. Plus, the energy consumption per person is increasing. If you look into yourself, 30 years ago only, or not 30, 20 years ago, or 30 years ago, do all of us have a mobile phone? No. Today, anyone does not have a mobile phone today? Everyone have a mobile phone. What does it mean? It means actually that's energy. Laptops, air conditioning, heating, cooling. So the energy consumption per person will be increasing. Energy consumption will be doubled by 2050. So what does the solution? The solution is, first one, to look into other source of energy and look also for cleaner source of energy. And also, the fact is 65% of global warming is due to energy generation and energy use. What does it mean? It means the way how we generate this energy and the way how we use it is not efficient. Means there is a lot of losses, because when we see emissions is just a form of energy. I think all of us know second thermodynamic law, right? So energy just transforms from one form to another form. So emissions is just a form of energy. So the energy how we generate it and then how we use it is not efficient. Right? So this is something that we have to look at. And I tell you this picture. This is just a small introduction. I don't know. I think some of you have been to the Fifth Avenue in New York. This picture I've taken in more than 100 years ago, in Easter time. What you can see from here, from this picture, I know we are engineers. We are not good in art. We don't appreciate art. But what you can see, this Fifth Avenue still look the same as of today. But what you can see here, where is the car? Maybe there is one, right? Only one car. Among all of this, what is this? Are all horse carriages. The mode of transportation in the last century, or the last 2 centuries, was the horses, right? In 1903, when Ford, the American who introduced the first car, people during that time, what they're looking for? They're looking for faster horses. Faster horses, not changing. But what happened actually, 13 years later, 13 years later, what happened? Where is the horse? See, this is what we call market disruption. How the market has been disrupted. Within 13 years have been changed. And then we look into this from let's take this picture and put it into our area, which is power electronics and power system. So if we look into this, what you can see, these are all motors, synchronous generators, right? Which is the current or the previous grid system. Previous grid systems, we have a lot of nuclear power plant, we have a thermal power plant, we have gas power plant, different types of power plants. Okay, this is what's happening previously. And where is the converters? Where is the converters? Maybe there is only one converter. Maybe there is one converter, which is maybe a small solar power plant somewhere. But this is what happened today. Oh, sorry, I'm moving forward. Yep. So this is what happened. Where is the synchronous generators, which is the main source of the inertia of the grid? So everything had been converted to converters. And that's what's happening to our grid system now. Our supply, electricity supply systems, there are more converters that have been integrated to the grid. And let me give you, this is what most of the countries are trying to do. In the last conventions, everyone is trying to push into what you call zero carbon. Few countries, actually only 2 countries have achieved the neutral carbon, you know, the small, 2 small countries there. But the rest, especially most of European countries and Western countries, they are still drafting the laws, the regulations. And some of them, like the UK, France, have announced that they will be reaching neutral carbon by 2035, 2045, 2050, and so on and so forth. So there is a long way to go. And in order for us to achieve this, in order for us to achieve this level here, there are a lot of things to be done. For example, by 2030, we need 60% of our globe steel cars have to be electric. Why? Because, you know, in the different sectors, we have the industrial sector, transportation sector, domestic sector, and the transportation sector. One of the main dominant of carbon emissions is the transportation sector. Still, most of our cars are still driven by gasoline. So in order for us to do this, 60% have to be cars. And in different sectors, you can see, in the electricity, in the industry, in transportation, in buildings, these are the things that need to be done in order for us to achieve the net zero carbon emissions. If we don't do this, you just forget it, you know. Whatever we do, whatever we plan, it will never be achieved. And on the other hand, for example, hydrogen, which is a very important source of energy, have to be introduced significantly. And also carbon capture. Carbon capture is also another way of how to reduce the amount of emissions. Okay, so the transitions, it happens at all levels. For example, if you look into the previous or few years back grids, what happens in terms of operation, production, market, transmission, distribution, and consumer? For example, if we look into the operation, most of our grid were always human operated. Today we are moving into machine operated. Every grid are machine operated. All in terms of production, we are moving from large productions, for example, 1 nuclear power plant. I think France is one of very good example of nuclear power. 70% of electricity in France is generated from nuclear power. 1 nuclear power is around 1 gigawatt. 1.5. Yeah, around 1 gigawatt system. So it's centralized, but we are moving into distributed, highly distributed, and not big size, smaller size. But the problem is low inertia. The inertia of the grid will be disappearing. So in all other aspects, central So there are a lot of converters. The traditional grid is not designed to understand how this converter works. because we are using the grid that's built in the 60s, 70s, and the 50s. These grids are not designed to handle this behavior of these converters, because these converters are very fast. They have a low inertia. So what's the solution? How we are going to design now, to design the converters, these converters, that be able to communicate well with an old grid. It's the same like you have your maybe grandfather, who never used a mobile phone in his life. And then you have a young child which is 15 years old, which is all his life is using mobile phone. How these two people can communicate? They talk different language. They're talking different, the different way of looking into things. So this is what happened. I'm not sure. I don't know how many people are in the power system and power electronics. So I hope you understand me. What I'm trying to say. So this is the main issues of all this. We moved from unidirectional to bidirectional. Not only the power, but also the data, the communication. We have a lot of communication between these devices. Okay, I'll give you an example of Australia. What's happening in Australia at the moment. So yeah, now it works. Okay, all right. So if you look into here, what I call the national electricity, market, how the difference between the old systems, the way called synchronous generators, which is mainly the gas, the nuclear, the what I call sources, and then the renewables. So in where is it? In 2000, say, higher wind and solar penetration been achieved from 38% in 2018 to 48% in 2019, and then up to 52%, means actually 52% of Australian electricity generated is from renewables, and is expected to increase. And now what happened? The government or the utility is putting a lot of restriction of adding new renewables because they cannot handle it. Now, if you want to build the house and sell electricity, you will sell it cheaper actually than the grid. So they don't encourage, not because of anything, but the grid system, the grid cannot handle this kind of penetration. The amount of renewables that's been injected to the grid from renewables is getting too much, and the grid is unable to handle it. So there is a need for upgrading the grid system in terms of control, in terms of management, and so on. So you see, the lower one was around 10 gigawatts. The total actually Australian power is around 30 gigawatts. So this is for by 30 minutes intervals. And you can see here it reaches in 2020 around 52%. Okay, this huge amount of penetrations actually create a lot of disturbance into the systems. And this is how it happens. So automatically, for the synchronous generators, which is having a high inertia, that comes from conventionals, it's decreasing year after year. Whereas we see the IBR, the inverter-based resources. Inverter-based resources is increasing, and at the moment we are somewhere here, around 50, 52, and 53, 50. I think the 2020 they have not released the report yet, but it's expected to be around 53%. So this is I'm not sure in France what is the percentage? 10%. Oh, all right. So this is the one of the major issues, and one of the solutions, what they are doing at the moment is trying to integrate the Australian networks with Fiji, with Indonesia, with Singapore, and connect to the Pacific, so they can sell this excess of renewable resources, because the existing grid is unable to handle this amount of power. So in terms of types of inverters, let's come to the topics where control, because in grid connected systems, it's very, very important. We have two systems. We have what we call a grid following and grid forming. Any inverters that is being connected to the grid, it have to be controlled either through what we call grid following, and this grid following, actually you are controlling the power and the current, okay, using and the inverter-based resources is acting as a current source inverter. Whereas in the grid following, this is acting as a voltage source inverter. Okay, so the trend of this is usually we use in the control loop, we use the phase loop to lock the frequency and the voltage to the grid systems. Whereas in the grid forming, which is the trend now, most of the research and the work is moving into what we call a grid, forming. Where here we control the injected power to the grid. Based on that, we will decide on the frequency and also on the voltage. So these are the main two forms actually. And this is the details. I'm not sure you're interested or not. So this is basically the control of the phase loops, how it's been designed, and then the power and the frequency, how it's being controlled. So we sense the power and the reference powers, and then we get the drop control and devise the control for the forming. And this is so in the terms of the PV topologies, what are the existing PV topologies? So this is just to highlight. It's been highlighted in popular mechanics. In 2020, the cost of electricity that generated from the solar is 1 cent, 1.35 cent per kilowatt hour. This is 2020, means that it's 6 times the cost of the solar. And this is actually in United Arab Emirates, where they installed these 2 gigawatts solar power plants. The cost of the electricity is 1.35. Compare, if it is from gas, it's 6 times. This is not the peak. The next one, 2021, new record. In a PV magazine, been announced, there is a tender which Saudi Arabia conducted, and it's 1 cent per kilowatt hour. Just to give you an example, one of the countries, Algeria is an exporter for gas. The current price, it's around 3 cents per kilowatt hour. But this is subsidized. Actually, the cost is around 10 cents per kilowatt hour. Means actually, it's 10 times cheaper. The electricity that is produced from solar. So actually, the break-even point have already been passed a long time ago. Okay? So when we look into this PV systems, what are the types of topologies and the configuration that we use when we integrate? Because in in a PV system, one of the main components is the inverter, and also the DC-DC converters that's been used. So we have either it is what we call double stage or single stage topologies. Either we use single high frequency transformers or low frequency transformers, how we integrate to the grid. And if we look into terms of types of inverters that we use, there are many of them. There are multi-stage, single stage, either it's isolated, non-isolated, and there are issues also. For example, if we go isolated, we have no problems on terms of safety. If we go non-isolated, yeah, the size becomes smaller, but the problem of leakage current will become an issue, safety become an issue, and other problems. In terms of configuration, we can have central, means one single inverter for one large big farms, or we can have different strings, few strings, or we can have AC module, which is we call it the micro inverter, which is attached to the PV cells. So there are different configurations. So this is actually, I took it from what I call Infineon, how they design their systems. So they classified based either it is centralized, where you can see a large PV panels connected in series and parallel, okay, to generate the amount of power, and then we have a single inverter. Okay, the good things about this, first one, you have a lower cost per watt, because in terms of cost, it's cheaper. But in terms of access to what happens at each string here, you will have a problem. Means you, if this one here having maybe shading, so this will impact the whole string. So actually you will have drop at all these strings. So the amount of power will be less. And then there's another solution, which is a multi-strings configurations, where you use multi-strings, and then you have a DC-DC converter. This DC-DC converter actually is used to do this MPPT tracking, to try to search for the maximum operating points of the system. And then you have single inverters. And then we have single strings. And these are usually for households, small applications around 10 kilowatts to 20 kilowatts. And then we have the PV modules. And then we have the micro inverter, which is around 500, 600 watt systems. So there are different configurations for different systems, and that depends on the applications where we want to use it. For example, if you ask which is the most efficient among all this, the micro inverter is the most efficient. Why? Because one panel, one inverter. So you operate your panel exactly at the condition of that panel. But the problem is costs. Cost factor, means you cannot have, you have 1,000, like we said just now, 2 gigawatt system. How many inverters that you have? It's a huge, but centralized inverters is maybe the solution in terms of cost. Okay, so yeah, now this is just a comparison. What are usually when we select which topology. For example, if you look into the central inverters, in terms of efficiency, very low. Or you can see mediums. String, very high. You see, the macro inverters also can be very high efficiency and high. But also they have very high costs in terms of, for example, MPPT. This is a very important factor, MPPT. In central inverters, it will be very low because you have a large number of panels connected in series and parallel. This is a medium, very high, because this is in individual, what you call inverters that are being controlled. So these are the architectures that can be selected and can. And then in terms of classifications, I don't know the time, Could you please tell me the time,
Still have 10 to 15 minutes.
I'm still in the introduction, I think we are colleagues, We are lecturers, Our job is to talk. So we know how to talk, If we don't stop us, we will never stop.
20 minutes.
So I have to jump then. All right, so I have not to stop,
Take your time.
All right, so, no, I think the discussions will be an important part. So, okay, the PV inverters, what you call classifications or topologies. There are quite a number of them. Can be classified in different. I have to skip this part, you know. Let me go to the grid integrations. Yeah. So for when we connect to the grid, that is actually this one. What I have passed through just now is the topologies that's been used in a different configuration. We have central, string, multi-string, and microfact. Different topologies that have been used in the markets. What we can also from this diagram we can see the industrial inverters actually have reached to the maximum efficiency. For example, when we do research, one of the important factors when we design something, we want to see what is the efficiency. You see, this is a market inverter, 98. Actually, you have only 1% to play with. So what the other factors we are looking for? We're looking for power density. Power density means how small is the inverter? What is the number of components inside the inverter? So the power density becoming a major issue of this. But in terms of efficiency, commercialized inverters already in the market already reached the maximum, 90, 98, 99%. But don't be too, too excited by these numbers. This is actually the peak efficiency. Because in inverter, there is an efficiency curve. And that's why inverter sizing, when we design inverter and the PV systems, inverter sizing is a very important point. For example, if you have 10 kilowatt peak PV panels, what is the inverter size? The inverter size may be 5 kilowatt. Not 10, because that is 10 kilowatt peak. Means at the STC, at the standard test conditions, at a perfect environment, there is no losses. So if your inverter is not operating at its operating points, you will never get this efficiency, maybe get 50%. And that's, in power electronics, the system is in series, you know, PV, DC-DC converter, and then we have the inverter. If this inverter efficiency is 50%, means your total efficiency is multiplied by 0.5%. The whole system will drop. So that's why sizing and selecting the components is very, very, very important, you know, for this. In the grid connections, as we said just now, there are two. Either we have either it is transformer or transformerless. So we have either we use a high frequency transformer, that is actually we solve the problem of leakage currents, or we use a low frequency transformers at the grid sites. There are a lot of standards that need to be complied with whenever we have different standards, especially for grid integrations in terms of harmonics, in terms of DC current injection, in terms of grid frequency and power factor. Means when you connect to the grid, and that's actually bring us to the first slide, when I say there is a lot of converters. So these converters, they will inject a lot of harmonics to the systems. These are some of the, for grid integration, some of the, considerations that need to be done, like synchronizations, earthing, power factor, power quality, and surge protections. These have to be, any inverter or any topology that have to be done, it have to comply with all these standards. In terms of wind, we also, what we see, there is an increase of power electronics in wind. 20 years back, there was zero power electronics in wind turbines. Zero means, actually, we don't use any converters in power in wind turbines. You see, today we are talking about 100%. Means all the power that is generated from wind is processed through the converters. And I can show you this. This is, I think, this is nothing. Okay, here. If you look into here, you see, the total power that generated from wind is processed through the converters. Means if you have a 10 megawatt wind turbine, so you will have a 10 megawatt converters here. So this is actually to show that's how power electronics have reached to the level to handle this amount of power. This was not possible 20 years back. And this is for AC grids and also the future. The future, we are looking into what we call DC grids. This is what will be in the future topologies. We're looking into directly from wind turbines, we can connect directly to the DC grids. Yeah. What are the issues? The grid integrations. Main issue is the fluctuations, because the problem of the wind, the same like solar, we have the fluctuations of power that keeps up and down, depends on the wind speed, and that is one of the major issue. Active and reactive power, okay, that can be what we call controlled. Okay, let me go to some of our research, what we do in our lab. You know, maybe that's one of maybe some interest. Maybe we can do some collaborations, whatever. See, okay, one of the work we're doing on designing the microinverters, and we have successfully designed this microinverter. So what actually, it's a multi-stage topology, okay, based on the flyback topology, and we design the control of it. And what we do here, you can see that we have managed to achieve the zero voltage switching and zero current switching during the turn on and the turn off. And we're able to get a very nice AC from the PV panels. And we tested the efficiency. We managed to achieve around 97% efficiency. And we believe it still can be improved further. And it can be better, especially when we optimize the design. This is one of the work that we're doing. We also work on MPPT for photovoltaics. You know the problem of these hotspots of MPPT. And this is when you put the thermal camera on the PV, if there is a shading. Because when you have PV panels, when a part of it is shaded, that will create hotspots. And with the time, this will damage the hot panel. So what we introduced what we call these MPPT controllers. So we designed the MPPT controllers. This is the PV panels. This is CP converters where we program an MPPT. We do the experimental validations. And that's what we achieve. If you look into here, we can see that because this is what we call different shading effect. When you have a different shading effect, you have different peaks. So we able to always track the maximum peak of the power. And you can see here it reaches the steady states at very fast, because I think I will show it in the next slide. And you can see achieving the maximum power. This is in the estimated power, and this is the actual power. See, it's exactly the same. So this is also an important topic. And then when we compare, we managed to achieve almost 99.78% efficiency of this MPPT. I know maybe from someone who does not work in the area, maybe will not appreciate. Because what is the efficiency of the solar panel? Do you know? 20%. What does it mean 20%? Means actually if you have 1,000 watts of sun, you get 200 watts. That is the 20%. So this is at the output of the PV panel. So we work after the PV panels. We are not allowed to lose anything after that, because we lost 80%. The PV panel losses is 80%. Or what PV panel can do is 80% losses. So 20% we get. That's 20%. Then we try to maximize it through using these MPPT controllers. So we achieve almost 99. And then also in this MPPT is the speed of tracking. Means we are able to track this at a very, very high speed. Also another project that we work on is on the inductive power transfer. Okay, inductive power transfer, not the electric vehicle itself, but in terms of transferring the power, because the current electric vehicles you have to plug in, you know, and then when you plug in, different countries have different plugs, different standards, different things. So we we are not the first one to do this, but there are many works actually going this. So we try to do this. We got a grant from Nissan. Actually, we have a Nissan Leaf we're working on to transfer this Nissan Leaf from what you call contact to contactless charging. So we're designing this, and you can see what is this wireless transfer. This is the coil, just a normal transformer, just two coils, and the power electronics part here. So we have designed the systems. So we propose this actually, this topology, what you call for using not using 3 coils. Because in the wireless power transfer, the main issue is the misalignment. Because you have 2 coils, you have the transmitter and then you have the receiver. You will have a maximum power transfer when these 2 coils are aligned, 100%. The moment if you are misaligned, you are going to lose. We call the electromagnetic field, so you have to capture all the electromagnetic field that generated on the primary by the secondary side. So one of the major problems is when the cars are misaligned, because different drivers have different how good drivers. Some of them they drive perfectly, but 90% of people doesn't park car properly, including ourselves, So we want to look into what will be the best coil shape. What is be the best coil shape to give us the maximum misalignment tolerance? Means even with 20%, 30% overlaps, you still can generate and this is what we do, the analysis for different types of coils. And we do the experimental validation. So we design the primary side, the secondary side, and you can see we use a lot of magnets. Okay, this magnet is to capture as much as possible the electromagnetic fields. And we achieve actually quite very good efficiency, which is around 92.5% efficiency. Okay, that's different misalignment tolerance. And with the 0 voltage switching also and 0 current switchings. This is on the wireless power transfer. Also, we start working on what we call dynamic charging. So the dynamic charging is like when you're having multi-pads on the road, and then when the car moves, because the problem with the charging of electric vehicle is the time. That is the big problem with the EVs. Now, 2 problems with the EVs. One is the charging time. Second one is the people doesn't feel comfortable. What will happen if I'm driving the car, suddenly stop somewhere? There is no charging stations. Or suddenly I stuck in the traffic jam for 2 hours. The battery finished. Or I am in France, for example, like today, -3, or maybe, I think France is okay, like Montreal or Quebec, where the temperature goes -30. When -30 means actually the battery capacity will reduce by 50%. Because, the electrochemical, the batteries are very sensitive to temperature. At a very low temperature or very high temperature, the capacity of the battery will significantly drop. So when you're driving on the highway, suddenly the battery capacity goes. So we're thinking of this dynamic. So we build this system. Actually, we analyze first, and then we build these systems to see actually how much power we can transfer. And the main issue of this is the power fluctuation, because when this is the transmitter here, when it move from one to another one, because from one electromagnetic field to another one, so you have the power fluctuations. So we need to maintain as much as possible the power fluctuations from as long as possible. So this is also, it's in process. The last one, the last project, I hope still on time. We're working on this. This is for large, because we see the trend now for photovoltaics in moving from small one, from kilowatt level, now moving to megawatt level. And as I said before, if you remember, most of these mega power plants, they're using central inverters. Using central inverters. And this is how it looks like. This is the existing one. So what we have? You will have PV panels, a large number of PV panels, maybe hundreds, 200, 300 panels connected in series, and then you have a DC-DC converters that's connected, and then you have some DC links, and then you have one PV inverter, big one, megawatt level, and then connect to the medium voltage of the grid, and then to the grid system. And then you may have few, maybe if you have gigawatts, so you'll have maybe a few megawatts inverters. Okay. One of the main drawbacks of these inverters, they are not modular. Modular means, for example, now I have 10 megawatts. Tomorrow I decide, because of the load demand, I want to increase it to become 15 megawatts. I cannot do. This is a single inverter. It's not modular. You cannot add. You cannot increase. You cannot improve on it. So that's one of issues. Another issue, if this inverter fails, the whole system fails. This 10 megawatt fails. So in terms of cost, it's cheaper. When we see cost per kilowatt, it's cheaper because we have single units. But if it fails, the whole system fails. So by driven by these problems in terms of modularity and in terms of failures, so we thought to introduce a new way. So we introduced this. So what you use here, we can see we're using the H-bridge topology, where you can see here we have, or maybe you can start from here. So we have PV panels, and these PV panels you can see connected to this half-bridge converters. Okay, so you have two PV panels connected to H-bridge, and this is how it looks like. So you have, this is optional. Boosting factor means to boost the voltage. It's optional, you can do it, or you can configure your inverters in such a way that can generate the amount of voltage needed between here, because you have VDC over 2, VDC over 2 here, and then we have converters. So what you can see from here, you can see that these topologies are modular in nature. Modular means this one similar to this, similar to this one, similar to this, and so on and so forth. So, and we devised the control. The main problems with this topology, the main problem with this is the circulating current, because you will have a lot of current circulating here. What happened? Because we have two, let me explain this. This is a three-phase system, three-phase, just showing one phase. So what will happen? You have this arm and leg. The leg is the whole system, from up, positive, and negative. So what will happen if you have power from here is more than the one from here? So what will happen? You have a problem of circulating current within the system. And then we have to eliminate that, because that is losses, So what we did here, we introduced the two control strategies. One is the energy balancing strategy, means we want to balance the energy between the upper arm and the lower arm, plus leg current control. In case there is a circulating current, we will eliminate it. Yeah. So then we did the experimental validations, and then we test the system. So if you look into here, so we changed the irradiance. All right. Okay. So we will change the power of one phase compared to another phase. So one phase we keep it okay, another one we change. So we change from one phase to another phase, and then we can see, you can see here, the current trying to compensate each other. So for example, here it's around negative 1. Here we have two currents, which is the red and the blue. Negative 1 is negative 2 plus 1, plus 2 is 0. So the circulating current will be always 0. So we managed to eliminate the circulating current within the system. And then we changed the, and you can see the power. We tested at 200 kilowatt system. 200 kilowatts, when the power is changing, it follows exactly without any any fluctuations. And this is the capacitors, the voltage and the thing. So also we done the test at extreme power level. Extreme power balance means 0, one is 0, another one is full. So you can see exactly they will balance each other. And you can see the what you call the power is dropping from 0 to, from the maximum to half. And also the circulating current, also you can see here the circulating current, they will cancel each other. Right? And then we do some dynamic performance tests of the systems where we introduce some disturbance, and the systems is able to maintain almost a constant voltage and also a constant power. Okay, I think that's all. Thank you very much. I hope it's not too technical or too boring. I hope you understand something. Yeah. Yeah.
Thank you, Professor, for this very interesting conference. Let's take maybe a few questions from the assistants. Someone would want to start?
Thank you, Professor, for this very nice talk.
Thank you.
I may have two questions.
Yeah, please.
The first one is about the micro inverter. When you have solar, it means that you are during the day. Most of people are outside their houses during the day. So if the microinverter is producing, you are either injecting this into the grid, if you are allowed, or maybe you can run some electrical components, but not all of them. So the problem of microinverters are linked for me to battery storage. Do you address this problem? I mean, hybrid inverters to deal with storage on batteries?
So the idea of whenever for microinverters, because if you are generating an AC, okay, if you are generating an AC, then the idea is either to use it as for the load or to inject it to the grid. Unless you will have a battery here. Means these panels will charge the battery or supply the load.
So
but the idea of the microinverter is to supply directly the load. Means, for example, you have an appliance at home which running on AC, and then you want to supply directly. So that's the idea.
You said that Australia is not anymore encouraging people to use
No.
renewables integrated to the grid. So are they encouraging for standalone applications?
Not
And
Australia. Not Australia is not encouraging. The utility companies.
The utility, yes.
Yes, the utility companies are not encouraging. So what's in the last election, we have just had the elections. You know, the Liberal, we call the Labour won the election, and one of the promise during the election, there will be a government, because our energy market is a private. You know, means I can buy electricity from different companies. Yes. You know, today I want to buy from this price, they will give you this price, this one will give you this price. So what we do, we switch. This will give me how much per kilowatt. This one I will switch. Every 6 months we do the switching. So you get save around $500 per year, you know. So one of the promises is to set up a government link company to do this, because they want to encourage more more integration actually for renewables. But the resistance, you know, Australia is it's a coal exporter, you know. All the minerals. Australia is one of the richest countries in the mineral exporters, especially the coal, you know. And there are a lot of power plants actually which runs on this. So there is they manipulate. I think the same like in France here you have the nuclear. So people from nuclear will supporting this till the end.
I mean, are they encouraging standalone applications? And if
now
we
they're
know
encouraging the storage.
Storage.
Yeah. Now we have a program called neighborhood storage batteries. Within one neighborhood, small area, we have a storage. We're forming like a microgrid.
Like in US.
Yes, we have a neighborhood battery systems. In one small area, one battery storage, big, 200 kilowatts. Another area, one storage, and that's actually can help in there.
Thank you very much.
Yeah. I don't know, in France you have this neighborhood batteries?
Not yet.
Yeah, I think
It's the beginning of collective storage solutions.
yeah, yeah.
We have a centralized system, and the battery are not yet encouraged right now.
Okay. All right. Thank you.
Thank you, Professor Saad. Please, I would actually like to know how you compensate the currents that the last work that you've showed us. The compensation.
The compensation, yes.
Yeah.
So what we do, we take some power from the upper, for example. If you have for example, this, for example, generating more compared to this one. So what we do, we flow some of the current from this to this. So they will balance each other. Because if you don't have the balance, what will happen? You will have a circulating current, because the extra current will circulate within the circuit itself. Yeah. Yeah. Yeah.
I have a question
Yeah.
about the hotspot on photovoltaic panels.
This one. Yeah.
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 So these hotspots are present when we have panels in serial or parallel. That's it.
Okay. This heat spot can be many reasons. Can be caused by many reasons. One of the reasons, because of the panel, when you have one panel, all the cells are connected in series. Yeah. Okay, they are connected in series, to generate the voltage required. So, in the PV panels, if you have one cell is shaded, shaded means it's covered. So what will happen? That's becoming resistance, right? So the total current in the series loop will drop on that cells. So what they do, the manufacturers, they will, to solve this problem, what they do, they put anti-parallel diodes. They will group a certain number of cells, put one parallel diode, so to bypass in case there is a shading. So, but the problem, when you have that anti-parallel diode passing, it will create different peaks. So you will have one peak, another peak, because if you have two diodes, you have two peaks, three peaks, and so on. So when you operate your panel, at which peak you are going to operate? Because we want the peak, the maximum one. So that's why this MPPT is designed to track the MPPT. But this here, this actually will cause by time, because there's a lot of current here. Because this conductor is designed to carry a certain amount of current. After some time, the heat build up, and they're becoming yellowish, and then brownish, and then it burns.
Okay, so you mean with current commercial PV panels and current commercial MPPT controller, we can occur this issue?
Sorry, I didn't get the first part.
With current commercial PV panels and current commercial MPPT controller,
yeah,
we can get this issue.
No, because that's the reason why we introduced these MPPT controllers. These MPPT controllers to solve this problem, to address these problems. Okay. Because the first commercial, they put anti-parallel diodes to bypass. Yeah.
Okay, thank you.
Thank you. I don't know. You see, if you look into here, so if you look, this is what I mentioned just now. So if you have like a partial shading, you have multi-peaks, 1, 2, 3, 4. So which one is we're looking into, because we're looking into what will be the maximum power of the PV panel, and this it exists at one point only. Among all of this, which one do you think? This is the one, because this one will give you acceptable current and acceptable voltage. It's not this one. This is here. Maybe it's higher current, but it's a low voltage. It's not the maximum power. So when you have these systems, we actually, what we do, we track where is the the maximum power, so we can extract the maximum power from the PV panels.
Someone else?
Yeah.
Thank you, Professor.
Yes, thank you.
Just now you said that you have done the research and the efficiency is like 98 or 99%. But how much power are we talking about? I mean, if you like 200 kilowatt for 99%, we still have 2 kilowatt of losses.
So this one you can see here. The test is being conducted, see. So we test it. This is the maximum available power. Okay? So this is the maximum available power at the panel because we test it at module level. At one module level. So you see, we are able to extract at maximum, is 100%. 100% means, but this is here we have to be very clear. Huh? The losses in here, we have ignored the losses in the converters, because there will be losses here. In the converter part, there will be a lot of losses, especially, this one here, we can switch it as zero voltage switching or zero current switching, but this passive component, there will be some losses. So what we tested the system, we tested at this, for example here, the maximum power available is 1 to 1. So we were able to extract 1 to 1.7. Here we are 102, it's almost the same. 44, here is 43, 40, this is the maximum power. So we test it at a module level. Yeah.
And one more question.
Yeah, please.
Just now you said that DC grid is the future.
Sorry?
Like DC grid
Yep.
is the future, but don't you think like in the converter itself, the limit is in the power electronics? Like if you want to convert like 20 kilo, we want to transport like 20 kilovolt, the power electronic itself, the semiconductor need to support the 20 kilovolt. But I don't think we have like the capacity like 20 kilovolt.
This one, just to give you an example, before this one, this one. The largest wind turbine now in the market? What is the largest wind turbine? 10 megawatts. One single unit can generate up to 10 megawatts. All of it is based on this. Is based on this. What does it mean? Means actually, it's a wind farm. This is a wind farm, Means there are a number of wind turbines. So one single here can handle up to 10 megawatt level. And as you know, in power electronics, we already have evolution in terms of semiconductors. We have moved from silicon to silicon carbide to GaN devices. So that actually helps to improve the power capability of the devices in terms of power handling, in terms of thermal, in terms of efficiency, in terms of frequency, because we are able to switch at a very high frequency compared to silicon-based devices. And about the DC grids, the future will be for either for DC or harmonized. Harmonized means you will have, for example, at home, you will have a DC bus. For example, let's take your kitchen at home. Do you know that kitchen 100% can run on DC? Fridge, because inverter-based fridge. Actually, you can supply from DC. Cooker, induction cooking. It's a what do you call it? You can supply by DC. What else? Whatever we call cookers. Everything inside actually can be converted to DC. Even at home, you see your TV. What is your TV? LED. LED actually you can run it on DC supply. You do need AC at home. Light, LED driver is powered by DC. So actually, there are a lot of appliances which can run on a DC. So the future, we think that will be maybe nano DC grids and nano microgrids. And these have to communicate with another AC microgrids and another AC nanogrids. So that's actually the future. Before moving to to the grid. That's the same as I said just now, the Ford. In 1990, all the horses. So people were looking for faster horses. So Ford, he doesn't follow that. He invented the first car. And you can see now, it runs for more than 100 years.
Okay, thank you.
Thank you. All right.
Thank
Yeah,
you,
please.
Professor.
Yeah, thank you. Please.
I have a question about can you use the, different energy sources in one grid? For example, using synchronous generator and the wind power or solar panel in one grid.
The main issue now is we're having less synchronous generators in the grid. So what does mean? The inertia of the grid is becoming less and less and weaker and weaker. Okay? Because the converter-based sources are low inertia or even zero inertia. So the best scenario, how to support this low inertia is through the storage. The only way on how to provide this inertia is to have enough storage that is connected to the system to support this inertia. So that's why now there is a lot of work on installing megawatt level storage. In Victoria, I think we have almost 100 megawatt storage system centralized. And then now the government is pushing, to install like 200 kilowatts in neighborhood systems. So this is actually to support the grid. Because there's a lot of penetration, like you see just now, 52%. And if it's not possible, like I think here in Europe, the best example is Denmark. Denmark, I think 50% or 60% of the electricity is generated from wind. And they are planning to reach 100% by 2035, I think. And beside increasing the wind, they're increasing the storage to support this. In any supply systems, always the countries, they're looking into diversify their supplies. So, for example, you have certain percentage from wind, certain percentage from solar, certain percentage from gas, certain percentage from hydro, certain percentage from different sources. So actually that will makes a better stability of the grid.
I have asked because the synchronous generator impacts the frequency of the grid, and that's
The synchronous generator regulates. The synchronous generator actually regulate the voltage and the frequency. Because as an operator, as a grid operators, you can operate, turn on, turn off, This amount, can you please, they call, by phone, or by WhatsApp, Can you please come in? Then turn on, then it comes in. But if the wind, there is no wind, what are you going to do? No one to call.
Okay, thank you.
Just a clarification in the same vein of the previous question, because I'm not sure I really understood the limits for solar power plant penetration in Australia, the stop to develop this kind of system. Is it because we reached the limits of the grid in terms of stability and that's why we develop storage, or for in terms of consumption, what is the real limit?
The reason is the grid cannot handle it anymore.
Okay.
The grid cannot handle it. And we start seeing a lot of issues in the grid. So that's why the shift is, I think the government from the politicians, especially we have actually one party called the Green Party. They are becoming very popular now because they want to push 100% renewables. But in order for us, because we are we are scientists, we are not politicians. We based on what's available. If you have a grid which cannot support renewables, what you can do? You push more renewables, you will collapse. When it collapses, there's no electricity for everyone. So there are two ways. Either, first one, you have to upgrade the grid, and you cannot upgrade the grid in 1 month or 1 year. It's a 50, 60 years taken to build this grid. You cannot decide in 1 or 10 years to dismantle this grid and then build another one. No, it will go gradually. That's how we think, okay? Plus, there are other solutions like storage, which help to stabilize the grid. So you have to increase these portions.
And what about grid forming in that equation?
Yeah. The future is for grid forming. It's moving to grid forming.
Maybe a very last question.
Yeah.
If you can come back to your slide where you were benchmarking the different PV power plant configuration, multi-string versus single string, and you talk about the economics trade-off between a single converter or multi-string. I was quite surprised by the power and the architecture you propose according to the power scale. You see what I mean?
Yeah, I got it. Let me put the slides.
Yeah, sure.
All right. I think you are referring to this slide, I think. Yep.
Yeah, this one.
Yep.
So for the big PV power plant, you basically choose a central inverter, and the risk of losing a complete PV string where one of them is shade. So you assume that in terms of cost efficiency, it's better to lose a complete string instead of choosing a multi PV strings with multiple inverter.
Okay, what I said, this is the current central inverters that's being used for large power plants. Means the current large power plants, megawatt level, they use central inverters. Okay, so one of the main issues, like I said just now, for example, because these are connected in series and parallel, you know, so there are many other issues, not only this issue. For example, the voltage level here also, in terms of safety, you are limited to certain voltage level. You cannot increase to more than 1 kilovolts, for example, at the input of the inverter because safety issues. Okay, so another solutions, which is a combination of multi-strings, but what we propose in my slides, we propose to modify this inverter to become a modular level. Where it is modular means you will have actually modular level like you're having multi-inverters working in parallel. Instead of one, because this one, this is, there are different topologies, but one of the topology is the 6 switch, the 6 switch inverter they use. They have sometimes back-to-back topologies, but some of them they use the 6 switch, the 3-phase inverter, which is very high risk, very high possible failure of the inverter. So another extended version, which is this, but here you have to use more converters. So the cost per watt for this will be higher compared to this. But in terms of power, this will give you more power for the same condition than this. Because this one you are operating on single string, single level. In terms of voltage, you have no issues. Actually, I have one slide I put it the last one. Yeah, see this one. Yeah, this is the problems. I listed some problems, this morning. What are the problems for this central inverters? That's how the centralized. For example, in terms of efficiency losses, like we said just now, because of central maximum power, because one central that controls everything, which is impossible to control. Low voltage rating of the PV, because of the safety issues, a lack of modularity. That's a major problems. One of the main actually issues, which is a lack of modularities of, that's the limitation of the switching power ratings, because you have a switch able to handle certain amount of voltage and current. If I want to increase further, I cannot. So these are some of the plus using the bulky heavy transformers at the output, because you will have a low frequency transformers. And for example, it's 10 megawatts, so you have to have transformers to connect to the grid. Yep.
Thank you.
Thank you. Yeah.
So how do you explain megawatt capable inverters have only 2 or 3 MPPT trackers? Currently in a commercial website, we can buy a megawatt inverter with only 2 or 3 MPPT.
Siemens is moving into this. Just to let you know, Siemens is moving to this. Oh, sorry. They are moving into this modular multi-level inverters. They already producing some of the inverters in the market. Because the central single inverter, already no more. They don't produce anymore. Most of them, they are moving into this modular topologies.
So this topology will be more and more present in next years.
Yes.
Okay, thank you.
Yeah, this is the future. Because not in terms of what you call efficiency, but in terms of, like I said just now, one of the major advantage of this, it's the modularity, and also the cost to replace or to repair. You know, for example, if there is a failure, okay, so the whole inverter has to go on. But if you have modularity, you just remove this, plug and play. You have a module, remove it, put another module, and the system works. Your 10 megawatt systems will never be affected. Plus, we have done some work on fault tolerance also. I think it's somewhere. Yeah, I think. We have done some because when you have this kind of switches, you can do what you call some fault tolerance, or introduce what you call redundancy. Some redundancy in order for you to avoid this fault tolerance. Even we have done actually a few tests. If even with one switch gone off, we're still able to transfer the amount of power that is in the systems. So this is one of another area of work also. Fault tolerance, yes.
Yes, another question regarding your the circulating current problem.
Yep.
We have this problem if we have different source in parallel and voltage mismatch between them. So why don't you use one of the source as a voltage source and the other one as current source, so you avoid this mismatch?
But as I say, that's now the modularity. Because you will have all the idea is, the main advantage of this topology is the modularity. You know, we want to solve the problem of single units.
And regarding your moving contactless charger, the different primaries should communicate between them because you have to switch off, switch on.
Yeah, this is a good question. Yeah. So this morning only we were discussing, this morning my students, we were discussing because when we have these pads, when we design these pads, these are coils, it's a coil, it's a coil, but we laminate it, So there are two conditions. One, we want to ensure power fluctuations between when the receiver moves from here to here, right? So there should be a constant power, almost constant power. But another problem, this coil will interfere with this coil when you on them together. So we were discussing what will be the best solution, either to put them further away. When we put them further away, then we have a problem of power fluctuations. So the power will drop and then pick up again. So one of the solutions which we found, maybe we will put some capacitive, because this coil will impact this. This will impact this. So we have to eliminate the mutual inductance, between these two. So we will put one of the solutions which we have discussed. We will put some capacitance to eliminate this between these two.
The frequency is constant, the same?
Yeah, this is already standardized. International standards is 85 kilohertz. You have to operate this your system at 85 kilohertz. So, and then also to switch between, because we found actually in terms of the number, because it depends on the speed of the car. How many coils you switch. So because the charging depends on the speed. So if the car moving faster, so you may switch more coils. Okay? And when the car passes, automatically this will switch off. Will switch off. We have the defined mechanism of this one. We switch off. When the car passes, it will turn off. Yeah.
Thank you. Maybe a very last question.
Yeah, your friend there. Yeah.
So SAB means single active bridge. Does the double active bridge exist?
Yeah.
So what is it?
Sorry.
What is it?
You're talking about this one? This?
Oh, this is a double active bridge.
Sorry, what's the question?
The question.
I thought you're talking about the wireless power transfer or about this.
No, I'm meaning SAB is a single active bridge. So is the double active bridge exist?
Sorry, you're talking about this one?
Yes, that's it.
Yeah, this is active. Yes, there is.
Yes, but is there a double active bridge on the market?
In the markets, double active bridge. I'm not sure. It means in the manufacturing, means there is a product. I'm not sure about this.
Okay.
I'm not sure about that one. Yes.
Thank you.
Thank you very much. Let's applaud our presenter for the very
Thank you very
exciting
much.
conference.
Thank you.
Thank you.
I don't know who's this watch. Someone put a watch here, I think, for me. Oh, okay. Thank you very much. Thank you.